So raster calculations. I said previously that we would look at this now, so let's do that. Cell by cell, just taking a number and applying it to each value in the raster, to each cell or pixel. Pixel if it's remote sensing data, cell if it's other data. We'll just say cell for the sake of simplicity here. So we multiply cell by cell, or divide cell by cell, or add, subtract, or do something cell by cell. So we take a value in this cell, and then we do something to it, and then that creates the new value in the next cell. So as we can see here, we're going to take a value, and we're going to square it. So 3 squared is 9, and then, 5 squared is 25, and then 4 squared is 6, so on and so forth. We just do it cell by cell. We don't care what the neighbors are doing. We don't care what any other layer is doing. We're just looking at the value that's there and do something to it. Boom, new value there. Okay, very simple. Why would we do this? This could be for stretching, image enhancement, something like that. Or it may be that we need to rescale our data because we've simplified it when trying to store it and we want to now get it to the right scale again. There are various things we might want to do here. Or the next method we looked at on that list in the previous section was the kernel analysis, where we take a window, a moving window or a neighborhood, and we move across the entire image. We go cell by cell, but we're taking in a collection of cells. So for instance, in this case, we're going to be calculating a new value for this cell here in the middle, but we're going to be looking at all of the cells, all 9 in this neighborhood, in this kernel. And if we do that, we take the average of all 9 cells. This is a 3 by 3 cell. This could be larger, could be 5 by 5, 7 by 7. Generally speaking, it's an odd number by an odd number. And we can then create a new value in this center cell. So instead of being 5 there, we now got 4.9. We've calculated the mean, the average, and this is quite often done for trying to find spatial trends in our data, for example. So we can calculate what's happening, the processes behind how do we get to this value. That's one reason for doing it. But we can do other calculations as well. As we see here, we can look for the median, it gets rid of noise. Also standard deviation to see how much variation there is within a neighborhood. Or more complicated edge detection, things like Sobel filters and what have you. Also work on neighborhoods. Data compression. So this is sort of connected to our neighborhoods in a way, because what we're looking for is things that are happening within a region. And this is not something always terribly useful for us, but more for the computer, although there are certain circumstances where we might want to do this in order to get more information out, because we are looking for areas of similarity. So when we look at data compression, this is zipping files, that sort of thing. There are many different methods, but we're going to look at a couple of methods here. This first one is run length encoding, and this is going to be more useful for classed data rather than continuous data. And so we're going along row by row, and we're looking for a run of similar pixels or exactly similar pixels. So here we have 7 blues, and then 3 reds, and then 11 yellows, and 5 greens. Well, instead of having to record blue, 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 red, 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 yellow, you just say, okay, blue times 7, then red times 3, then yellow times 11, green times 5. You only need to store that information rather than this whole length, which means we can compress the file. It becomes much smaller, but it tells us a little bit about the relative size of these different classes in this. It's kind of interesting, but this is generally speaking used for compression. We can also see that there's a bit of we need to be careful when using it, and also you can see why this is better with class data rather than, say, continuous data, because if we have continuous data, then the value in each here varies all the time, or usually does. And so we get one blue, and then we go on to something else, and then it's one red. So we need to say this is a blue one, and there's one of it, and this is a red one, and there's one of it, and this is a yellow one. So actually we end up storing more data because there isn't enough repetition in there for this to be a particularly efficient method of data storage. So that's one method of data compression. Another one is this quad tree. Now this is only going to work with particular types of discrete data, again, where we're saying something exists or it doesn't exist. This also is a way of having a variable resolution, sort of, in our files. We can use something similar in particular types of meshes, which you can get back to later on in more advanced courses. But here we have an image, and this is a very basic, simple image where mostly it's sort of this white class, whatever this is here, lighter colored up here, and then this darker gray down here, with quite a detailed edge to this area going around here. And how would we store that information? Obviously, if we want this level of accuracy everywhere, we would actually be storing many more pixels. But nothing's happening here, so why store so many pixels where it just says empty space, empty space, empty space? That whole sort of repetition problem. Can we get around that? Well, we can, sort of partially, by using this quad tree construction, whereby we first of all divide the image up into 4 parts. And we look at the center of that. And we say, we're at this first node, this central node here. We go to our next one and we say, and this O here is saying something's happening. You need to investigate this further. There's some variation here because at this point none of these 4 were similar. Okay, so then we go to this upper left corner here, and we're looking at this one, and it's saying exactly the same thing. Yeah, this is actually kind of fractal there, isn't it? Something's happening here. You need to look, examine this further on. You need to go into more detail. Some things, there's more information to be had. And this one, this next other node here, it's saying, well, it's white. Let's just completely fill that whole thing up with white. There's no more information to be had. And then we go down to that one, and that's all grey, black, or whatever the alternative is there. And then we go on to this one. So, oh, there's more to be said here. You need to do something. You need to look at this in more detail. So we need to go on. We need to break this one down. All right, so let's break that one down. Let's move to that part there. And then we do the same thing. And it says, okay, you need to break that one down. And then you need to break that one down. And in the end, you just do this step by step. You're following the same construction, just going down and down and down where there's information to be had. We can see here that we could stop. And this one, here we have these small details here that you can see. Whereas these ones, they don't have such information. They stop at this larger ground sampling distance, as it were. Whereas these ones continue all the way down. And then the information they get stored in the structure, because we are logically following this structure, is this long string of, and that's how we store the quad tree. More nuanced information, different details, like different layers, aren't going to work in the same way. And we only have this, we can't have continuous data in here. We only have this discrete on or off state. But it's stored, and we can have a variable scale in the data.